Welcome everyone, I'm Dániel Berényi, I'm one of the members of the GPU laboratory, and yes, we are organizing this conference and it's good that all of you are here. And in this talk I'm going to talk about one of our long-term research topics into optimization of different algorithms, particularly linear algebraic operations, and we are investigating the question about improving data locality. Similarly, that the earlier talks were revolving around. And this is a common topic with András Leiteregg and Gábor Lehel. And let's see what we have here. So we are working in a few buildings down the road. We have quite a lot of hardware, and we are also providing developer support. So people come to us with questions how to write good code, how to make things faster. And so we see lots of codes written by our colleagues and other research people. And they are very good domain experts, usually, who have no time to go into the details of programming. So go to learn about every little hardware details, about memory management, about parallel instruction sets, and also they do not have time to delve into the software engineering topics, which APIs to use for different kind of parallelism. So we try to go into the direction whether we can build a tool that would automatically help them with the optimizations. Because lots of the code that gets written is, well, could be better and utilize the ever-changing hardwares better. So I think you already know the hardware hierarchies that we have. So we have large computing centers, just like the one that in this building. It consists of lots of clusters of computers using multiple devices, CPUs, GPUs, also other acceleration units. And each of these has different number of execution units that manage lots of threads. So we have a large hierarchy of computing hardware, and we need to write software for this large pyramid of hardware. So how we can do that? And the particularly interesting topic is the arrangement of data in this hierarchy. So we have the registers that are the nearest data storage units next to the computing units, and threads operate on that, but some group of threads have some shared memory that is faster than going out to global memory. There are caches, and there is the on-chip device memory, but sometimes we need lots of data, and it does not fit into these small memories, and we need to go out to external storage, whether it is a disk or a tape. So we somehow need to arrange all of our data based on how often we need that for the calculations, and this is a non-trivial task. And the question is how to do it so our codes would be as fast as possible. So the specific example that we are usually aiming at is the question of linear algebra, because as you know, 70% of every calculation in the world is somehow related to linear algebra. The other 30% is Monte Carlo, but we are not talking about that. So every physics simulation, the neural networks, and much of the data modeling and data analysis is somewhere at the end, it turns down to linear algebra. And there are really good hand-tuned libraries that basically cover every hardware. This is for so most of these libraries are somehow related to the BLAS. It contains fixed primitives that you can use to express linear algebraic operations. But the big problem is that these primitives are not easily composable. They're not flexible enough. If we need some specific operations for our calculations, it is not easy to modify them because they are hand-tuned for particle calculations. And on the other hand, there are C++ template libraries. I have wrote some examples here, but somehow they are still too specialized for our needs because, for example, in physics, we need arbitrary dimensions of tensors, and we need to express n-ary summations and products and crazy operations on them. And somehow all this stuff is still too limiting. And the question is, can we have some good expressive language for this and still get the benefits of the hardware? So yeah, we need linear algebra and more. And the question is whether we can so what primitives are suitable for automatic optimization? This is the big question. And surprise, surprise, there are no surprises. These are the same primitives that are usually used in the C++ standard library as we saw earlier, or basically every other related construct. So we have element-wise operations. For example, we have an array, and we have some arbitrary function that we are mapping over each element separately. We can do this with more arrays. For example, this zip function could take 2 arrays and apply a function pairwise of the elements. And we can reduce an array with an arbitrary binary function to a single resulting element. Okay, so we have these higher order functions. They are in the standard library, but we would like to compose them, and compose them in crazy ways. Every way is possible, because at the end, when we are writing code and writing real-life simulations, basically everything would come up, that every combination that is possible. So let's take a look at how do these things compose. When we have maps, think about C++ std transform or things like that. When it is operating only on one element, there is no problem. It is composable. We can compose arbitrary number of single array operations next to each other into one single transform, and get and all the temporary objects could be eliminated, and no problem arises. We just need to compose the function that we are using on the elements. But what happens when I have a zip, when I somehow combine 2 arrays? It turns out that with regard to the composition, this is not closed. Because when I take this single array operation and then try to compose it with this binary zip, I do not have a primitive between these 3 that could cover the resulting operation. So it is a bad thing. We are out of the language that we just constructed before, so we need some generalizations. And the way out is to generalize these operations. For example, we could introduce this NRZip that now takes any fixed number of arrays, for example, n arrays, and takes an n-array function and element-wise composes just like before. But now this is closed under composition. I could compose together as many n-zips I would like and still get one transformation, one parallel algorithm at the end, and no temporaries. You can see on the figure on the right-hand side that we can take a 3-array zip with a 2-array zip, compose them together, and we have a 4-array merging zip. Okay, and we can do the same with the reduce. Before the reduce, I could compose any number of these zips and maps. We have now a reduction operator, the first one, the binary function that will summarize the values. But before that, I have an n-array function that somehow combines n number of arrays. And now this is so nzip was really closed, and reduce zip could compose any number of nzips before that point. But at the end of the reduce, we get a single element, and there we always need to call another higher order function if we would like to compose that way. But this is not the end of the story. So we would like to optimize somehow all the possible combinations that would arise combining these primitives that I have shown you. And there are different types of these optimizations. The ones that I've shown you already are the fusion rules, when we somehow put together these higher order functions into a single higher order functions. But there are also subdivision rules. For example, I have an array of 4 elements. I can change my view a little bit and take it as a 2-element array containing 2 elements each. And if I use this subdivision repeatedly, I can have a hierarchy induced on the array. So I can have, for example, n number of depths with a different number of elements, with different number of groupings. But the good thing is that this directly transforms into a splitting of the higher order functions. So as you can see on the the equation, I had a single map operating on this blue array, but I can replace that with two maps nested into each other, operating on the outer layer and the smaller chunks. And I could use this splitting repeatedly as many times as I would like. And the other interesting rules are the exchange rules. If I have nested, for example, two maps, I can exchange the order. Okay, so only the logical layout will change, but I can play around with in which order I am carrying out these operations. And this gets particularly interesting when there are different higher order functions there. I have a map and a reduce inside. I can exchange their order with the cost of flipping the array, the logical layout of the array. Okay, so let's take a look how this plays out in practice. For example, take this matrix vector products example that is could be done in two ways. The one way is the traditional textbook way. I'm taking rows of the matrix and calculating the dot product with the other vector. So inside this redo zip, this is the reduce after a zip with the plus and the multiplication. This is the dot product. And I'm repeating it for each of the rows. That is the outer structure. This is the zip part. But I can do it otherwise. So I can take the columns of the matrix and multiply with each scalar element of the vector. I get a new set of vectors and add them together. And this is, if you look carefully, just the exchange of the higher order functions and a transposition of the logical structure of the matrix. So I flip the rows to become columns. So if we are playing around with these higher order functions, we get different rearrangements. For example, if I induce another level of hierarchy on the vector and the matrix, I can have 6 rearrangements of the matrix vector multiplication shown in this figure. So if you take a look, you can see that the uppermost left figure shows rows subdivided. But then you see that there are columns subdivided into rows. At the right top, columns subdivided into columns, and so on and so on. So there are different rearrangements, and they would have different performance at the end. So at this point, let's not measure the matrix vector multiplication because it is not difficult enough. Let's take a look at the matrix multiplication. There we have another layer of map. So we are mapping on the rows of one of the matrices, mapping on the columns of the other matrices, and then calculate the dot product over the column and the row. And use these exchange rules that I've introduced earlier, and we can have these 6 rearrangements. This one at the top is the naive implementation that every student would write. And the performance on some system is this one. It is like 5 seconds. But if we calculate the other reorderings, we see that there is a much better performing variant when the reduce is exchanged with the map over the columns of B. So it has a much larger data locality, and we gained a factor of 10 compared to the naive version. Okay, so if we repeat it further, calculate even more subdivisions of the matrices, we can get more and more candidates that we need to compile and measure. And the naive algorithm was 5 seconds, and if we go up with the subdivision, we could get down to something like 180 milliseconds. And the good point was that we could just blindly use all these identities that I've shown you. There is no any further thinking necessary. We need no information from the hardware. The only thing we need to do is just compile each of the candidates, measure them, and then at the end use the one that was performing the best. Okay, the problem is, of course, this factorial here. Okay, this is bad because we need to really compile and run lots of candidates. And the answer is, if we have really a simulation when the traditional optimizations are not enough, because it is going to run for years, CPU years and GPU years, we really would like to optimize all the possible things. And the compilers that we are using today somehow do not have enough parameterization to let them compile everything as long as they wish. I don't care if my code compiles for days, but then I need the last percent in the performance to be there. So here, this n factorial is really, we are not talking about hundreds, we are not talking about 6 or 7 or 8. I've shown you the hierarchy level. We do not have 12 levels of hierarchy. We just have some 5, 6, something like that. And for that, this factorial is not that big that would cause any problems. Okay, so we can use this to get something, but I would like to talk a little bit about what is in the background. So basically, we built a compiler in Haskell. It is using structured recursion schemes. So basically, we need to transform ASTs into different ASTs. And for that, we use these catamorphisms and other nice things from category theory. This helps us to really create an extremely modular compiler. And it is really easy to add the new paths and add features to that. And with these recursion schemes, we have implemented this pattern find and replace. So all the identities that I've shown you earlier are described as patterns that need to be found on the AST and replaced if some conditions match. And at the end, we generate from the Haskell embedded language C++ code. We can generate, for example, for CPUs and GPUs using the SYCL standard. And using this toolchain, we can create all these different rearrangements. The problem is, of course, that this n factorial could be done better, but for that we would need in the future a cost model-based heuristics. So we need to assume something about the hardware. We need to assume some costs of, for example, the size of data that could fit in one of the memories, the bandwidth, or things like that. And then we could cut down on the number of candidates that would need to be measured and compiled. And the data the measured time data that I've shown you was just for one level of the hierarchy. It was for the cache, the first memory, and we need to scale this up really for the other levels. But the point is that these operations are somehow general enough that they could cover all the different levels of the hierarchy described earlier. Just the implementation need to be aware of how to implement a map at the different levels of the hierarchy, how to implement a reduce on the different levels of the hierarchy. And nice, we could somehow cover all these tensor operations, but there is another big topic or another great set of operations that are quite usual, known as the sliding window computations, when I have some operation that accesses the neighboring elements like convolution or others, and we need to fit them also into this language so we can reason about the compositions and combinations of convolutions with all the other maps and reduce and things like that, and aim for some closeness there also. Okay, so if you want to look into more details, the code of the compiler and some sample codes are in the GitHub repository. It is somehow a little bit behind what we would like to have, but all of the research is propagating there. We have a publication about the results and details of this optimization for locality, and if you have some questions, I can come back to that on the backup slides. Thanks for your attention.
Thank you very much, Tony.
Really a great presentation, thank you. What I was thinking about your ideas about the cost model. What is your progress towards finding heuristic cost model for your work?
Okay, we have not yet really thought about that, but there is some, so there are already tries in the literature about that, and it is really based on the sizes and bandwidths. So if we have some rough numbers on that or limitations on that, there are some established methods how to do that. But we have not really gone into that into detail at this point.
There is a recent paper about that. Maybe you can, or maybe you know it. It's Blechloch.
Let us know. Let us know. It could help.
Okay, further questions? Then maybe I can ask the same what I have asked already. That what was your motivation in order to go to this direction of development.
Yeah, basically solving the differential equations. So at the end, when you discretize the differential equations, partial differential equations, you have some crazy tensor constructions with a different number of tensors, different set of indices, and we need to somehow express it without any constraint on the dimension or the number of arguments or things like that. So this was the primary aim, and the complications come when we need to somehow map this to cache and map this to the local memory and things like that, and we don't want to do it manually, because the next time I'm changing some part of the equations, I will need to redo all the optimizations that I did just because something small changed. We don't want to do that, we want to do this with some tooling.
Okay, any further remarks or things? Okay, if not, then let's thanks to Dániel again. And,